Hey everyone, we're just about to start chapter 8, and this is the general topic is hypothesis testing, and this is going to occupy us for about 3 weeks or so. Um, and it's the major part of inferential statistics. So in a sense, we're getting to the real heart of what this course is for. Um, And this first section, 8-1, it's just called Basics of Hypothesis Testing. So it's mainly some sort of big picture ideas about what it even means and some definitions. We are going to do one kind of full example that shows the main aspects of hypothesis testing. And so we're going to do this section in 3 parts. In the first part, we're focusing on again some very basic definitions and concepts. By the end, you're going to know all these terms, so null and alternative hypotheses, test statistic, critical values, p-values, and you'll see how we state a conclusion properly at the end of a hypothesis test. I mean, in a basic word, a hypothesis test is, well, we have something that we think might be true, and then we get some sample data and we test, is that thing true? So at a basic level, that's the same thing that, scientists, doctors, they're doing it all the time. I think something is true. Let me get some observations, check if it actually pans out. But we just have in statistics, we have a very specific way of doing that. And so it's going to take us a while to lay out how that works. Okay, but let me give you the first introduction here. What is a hypothesis test? So let's think about flipping a coin. Now, what's a fair coin? A fair coin is a coin that comes up heads 50% of the time in the long run, right? And normally, if you had a coin, you would just assume it's fair. It's just a normal coin. So we would, if you received a coin, you would normally treat it as fair unless you had evidence to the contrary. So in other words, to begin with, you would accept this statement, H0, this coin is fair. And that's called a null hypothesis. Um, so we use the symbol 0 there because null is another word for 0, null hypothesis. So a null hypothesis is what you might call a default assumption. It's what you believe kind of at the beginning in the absence of any other information. Okay, so you would accept this coin is fair unless something proves otherwise. Now, suppose you flip the coin twice and it comes up heads both times. Now you think, okay, it shouldn't be heads all the time, but just 2 heads in a row, would that be enough to make you agree with the following? H1, this coin is biased towards heads. You flipped it twice and it was heads both times. Seems like maybe it's biased towards heads. And so this is called an alternative hypothesis. Alternative hypothesis. And it's something that you might believe if there's enough evidence. Something it's something you might believe instead of the null hypothesis, instead of the null. But only if you have enough evidence. If you have strong evidence. And think about this now. If you flip a coin twice and it's heads, is that strong evidence that it's biased? No, right? Because you could very reasonably get 2 heads just by random chance, even if it's fair. So probably we would say, no, it's not adequate evidence. What is the probability of getting 2 heads? Probability of getting 2 heads. Well, this is the kind of problem we did quite a lot in the past, and so that would be actually 1/4, which is quite likely. So we could easily see 2 heads just by random chance. It should happen about with a 25% chance. So it's not enough to convince us that it's biased towards heads. Okay, now what if you flip the coin 10 times and it was heads all 10 times? What about that? What is that going to be enough evidence? It might be, right? So let's think about this. What's the probability of getting 10 heads in a row if it's fair? So assuming this is I should have said this before. Assuming that it is fair, the probability of getting 10 heads in a row would be a half times a half times a half, right? There'd be 10 of these. Half to the power of 10, which is really small. It's very small. So with it, if I write it as a decimal, 0.000976 something something. So that's very unlikely, right? So what we would say is if the coin is fair, if the coin is actually fair, getting 10 heads occurs with a probability of, with a very tiny probability. It's that number we just wrote. So that means that seeing 10 heads would be seeing a rare event, which should make us reject that assumption. So then observing, I should use the correct word here. If we observe that 10 heads, we have therefore seen a very rare event. Which shouldn't happen very often. So we would reasonably, let's just say we would reject the initial assumption. And you'd say, well, it's not fair, I guess. We reject the initial assumption. So the way we put this is we say we reject the null hypothesis. We would reject the null hypothesis. And therefore what? We would therefore accept that it is biased towards heads. And we would accept the null hypothesis. Sorry, I said null, but the alternative. So we would say, yes, it is biased towards heads. And you might be thinking, well, how do you really know it? How do you know it's biased towards heads? You've only flipped it 10 times. That's very true. It is possible that it really is a 50-50 chance, and yet, just by bad luck, you get heads 10 times in a row. How likely is that? Well, it's exactly this likely. It's not very likely. So, while, in other words, chance by itself is not an adequate explanation of the 10 heads. The null hypothesis plus chance is not an adequate explanation of what we observed. So therefore we reject the null hypothesis. So all right, so that's the kind of logic we're going to use over and over again. But we're going to make it a bit more formalized and more of a procedure that has a step-by-step process. Okay, so let's get some definitions going here. What is a hypothesis? A hypothesis is always a statement about a population parameter. It's a mathematical statement about a population parameter. Such as It could be p, it could be mu. It can also be p1 minus p2. Maybe we have two populations and we're comparing the proportion of the two populations. Or it could be mu1 minus mu2. We have two populations and we're comparing the mean value of something, their mean income. We could say, what's the difference between how much money Canadians make versus Americans? Then we'd be comparing the mean for one Canadian minus the mean for two US. And we could also do sigma squared, or even you could even do sigma 1 squared minus sigma 2 squared. Now in this course we're not going to do these ones, but we are going to do all of these. We're going to be studying hypotheses about a single population, which would be these ones, and we're going to do where we have two populations, which are really important ones. So for example, let's say you're testing a drug, testing a drug for COVID-19. You're going to have two populations, right? You're going to have people who took the drug and people who didn't take the drug. And we want to know what proportion of these people get better versus the proportion of people who didn't get the drugs. Maybe they don't get better as they're less likely to get better. So a null hypothesis is, again, the kind of default assumption. It's the statement that nothing is happening, or there is no difference. So for example, one null hypothesis might be that the proportion is a half. So it's saying something is equally likely or not to happen. Or it could be that the proportion of one population is the same as the proportion of another population. Or it could be that the mean value is the same as the mean value for the two populations. Or it could be that the mean is 0. Now, a null hypothesis always involves equals, always uses the equal sign. It's a specific statement that says something is 0, something is a half. And an alternative hypothesis is the more interesting thing, that's saying, no, something is happening, something unusual is happening, there is a difference. So for example, you would say the proportion of people who, let's say, recover from COVID-19 is greater than, so let me be more specific here. Let's say this is the proportion of people of, let's say, a treatment group, proportion of a treatment group who survived the illness. And then this one is the proportion of the, let's say, the placebo group who survive an illness. And if this is saying that if you get the treatment, you're more likely to survive. The drug is working. So that is an example of an alternative hypothesis. It's saying that there is a difference. And the alternative, it involves, it's always stated in terms of a not equal, of an inequality. It involves either less than or greater than, or it could be just not equal. Okay, so that's one clue to what kind of hypothesis are you talking about. Okay, now let me just add. I think that's okay. Let's leave it like that. Okay, so by default, if you have if somebody says, "Hey, try this drug, maybe it'll help cure COVID-19." If you're skeptical, you would say, "Well, maybe, but let's begin by assuming that it's no more effective than a placebo. Let's assume that there's no advantage for taking this drug. We hope it does, but we start out with the assumption that it doesn't do anything. and we need to be convinced. We say, well, maybe, but prove it, right? Convince me. So by default, we adopt the null hypothesis unless evidence leads us to reject it. So think, in another way we put this is think innocent until proven guilty. So that's how our legal system works too, right? So in the law, the null hypothesis is that the person's innocent, right? We assume they're innocent unless there's evidence. The alternative would be that, nope, they're guilty. So we always assume somebody's innocent unless there's evidence that they're guilty. Okay. Now, question, what is considered adequate evidence to reject the null and say, no, you're not innocent, you're guilty? Or, no, the drug isn't the same as a placebo, it's better than a placebo, right? What's the bar there for what counts as adequate evidence? Okay, this is tricky, but let's try to do this. So here's the answer. What we do is we assume the null hypothesis is true. So assuming the null hypothesis were true, that would imply that certain outcomes of our experiment would be very unlikely to occur. So given that the null hypothesis is true, some outcomes would be very unlikely to occur. If we then actually observe one of those rare outcomes, then that means we have a good reason to reject the null hypothesis. Then we have adequate evidence is when we observe what should be a rare event. Let's write that down. Adequate evidence is when we observe what should be a rare event if the null hypothesis is true. What should be a rare event if the null hypothesis were true. It sounds weird to say were, right? But I think that's correct English. It's called the subjunctive tense. If the thing were true. If I forgot the word null. That's the most important word. If the null hypothesis were true. Adequate evidence is when we observe what should be a rare event if the null hypothesis were true, and so we reject the null hypothesis. Okay, so let me give you an example. Like let's say suppose a coin is fair. That would be the null hypothesis. If we observe 100 heads in a row, well, that's extremely rare, right? That should never happen. If we observe 100 heads in a row, then that would be adequate evidence that it's not fair. I forgot a step. If we then observe 100 heads in a row, which would be extremely unlikely, possible but extremely unlikely, then we conclude that it's not fair. Okay, so an open question still here is, what do we mean by unlikely? And that's this. So the level of significance, which is denoted by alpha, it's what we consider unlikely. Let's put it this way. It's our definition of unlikely. So typically we would choose, it's the same alpha that we used for confidence intervals. Typically we choose alpha equals 0.05. So we're saying that, i.e. we're saying that 5% is what we consider unlikely. So if we see something, if we observe something that should occur only with a probability of 5% or less, we would say that's evidence that our assumption is false. Okay, now the p-value, actually this should be a capital P, so let me change that to a capital P. The p-value for an observed sample statistic. Okay, so let me just clarify. An observed sample statistic is basically that, i.e., that's the it's that comes from the result of our sample of our experiment, the result of our experiment. The p-value for the observed result of our experiment is it's the probability that an outcome as extreme or more extreme than that observed outcome. Okay, it's hard to put in words. The probability that an outcome as extreme or more extreme than that observed outcome. The probability that an outcome as extreme as that observed outcome occurs given that the null hypothesis is true. So let me give you an example. Let's say here's an example. This p-value is probably the hardest concept in this whole course, so don't worry if it's a little bit overwhelming right now. But so here's an example. Suppose you flip a coin 100 times. And let's say you observe, let's say 70 heads. The p-value is going to be, the p-value for that observation is going to be the probability of observing at least 70 heads, which we could work out with our binomial distribution, but for the moment we'll just leave it as it is. So it's the probability that of observing an outcome at least as extreme as the one we actually observed. I think I need to write that. That's what I wrote is still too garbled, so let's try that again. It's the p-value is the probability of observing an outcome at least as large, at least as extreme as the actually observed one, the actually observed outcome, given that the null hypothesis is true, given that the null hypothesis, assuming that the null hypothesis is true. So in other words, it's calculating the probability of getting that many heads or more, assuming that the coin is fair. Okay, so it's like we're saying, okay, we got 70 heads. That looks strange, but let's try to give it the benefit of the doubt. We'll say, well, maybe it is fair. I mean, we certainly could get 70 heads if it was fair. But we'll say, okay, if it really was fair, what's the probability of getting that many heads or more? And if we did the calculation, we'd see it's actually very unlikely. So probably we didn't just see this by chance. It's actually showing us that the coin is not fair. Okay, hope you caught that. Okay, a couple of questions here to solidify the terminology about null hypotheses. So, are these statements valid null hypotheses? Could we use these as a null hypothesis? Why or why not? Okay, so let's try this one. In a sample of students, the mean pulse rate for the men is equal to the mean pulse rate for the women. So let's see, in symbols, what would this say? In a sample of students, the mean pulse rate for the men, let's call that x1 bar, it's a sample mean, is equal to the mean pulse rate for the women. That's how you'd say it in symbols. Is this a valid null hypothesis? Well, normally we might write it like this, maybe, equals 0. But no, it's not valid. Why is it? Why not? Because it's not about a parameter. It's about a sample statistic. It's not about a population parameter. Hypotheses are always about the population parameter. So if it were the statement mu1 minus mu2 equals 0, that would be a valid null hypothesis. So the null hypothesis is always a statement about the population, not just about the sample. Okay, let's try this one. The average weight of newborn boys is the same as the average weight of newborn girls. So let's see. This is not saying for a sample, it's saying for all of them, right? So the average weight for newborn boys is the same as the average weight for newborn girls. So it's saying in symbols, it's saying that mu1 equals mu2. And that is valid. So we could put it in the form mu1 minus mu2 equals 0. So yes, that is a valid statement about, and it has an equal sign. That's a critical thing too. Uses equals. So it's a valid statement involving equality about population parameters. So that makes it okay as a null hypothesis. Last one. The proportion of cars that are white is higher in British Columbia than in Newfoundland. So the proportion of cars that are white, so let's call it P1 in British Columbia, is higher than in Newfoundland. So we have a proportion for Newfoundland, and in symbols, this statement is saying P1 is greater than P2. So this is good that it is about population parameters. It's not just about a sample, but it does have a problem, which is it doesn't involve equality. It involves greater than. So this would actually be the alternative hypothesis. This involves inequality. Inequality. So it would actually be the alternative hypothesis. The suitable null hypothesis would say that they're equal, that the proportion is the same in both provinces. So null hypotheses always have a kind of boring kind of aspect to them because they're saying these are the same or nothing is happening. There's nothing new. It's the alternative hypothesis that's saying, no, this is better or this is more, this is different, something out of the ordinary is happening. Okay, so we'll leave it there. In the next video, we're going to go step by step through a more or less full-scale example of doing a hypothesis test. All right, see you then.